Hello, today I am going to solve my homework 9. Okay, let's start. Show that set of decidable languages is closed under union. Let's start with the first question. Question 1. A statement: if L1 and L are decidable, 1 and L2 decidable languages, then L1 union, then L1 union L2 is also decidable. Why it's true? Let's explain it. There is a decider D1 that decide L1 and decider D2 that decide L2. Okay. To decide whether a string omega is in L1 union L2, we can design a new decider D. Okay. D1 decide L1 and D2 that decide L2. Okay. Let's design new D. Let's simulate D1 on input omega if D1 accept. Okay. Simulate D1 on input omega if D1 accept then omega under so we immediately accept omega. Okay, then if D1 rejects, we then simulate D2 on omega if D1 D2 if D2 accept then omega L2. So we accept omega, otherwise we reject. Okay. D always halts since D1 and D2 are decider and correctly decide membership in L1 union L2. Okay. Therefore, L1 union L2 is decidable. Okay. Then statement 2, show that a set of decidable languages is closed under complementation. Okay, let's remove homework. Question 2. If L is decidable languages, then its complement L2 also decidable. Okay. L complement. Okay. There is a decider that decides L. Okay. Decider that decides L. We can build a new decider. Okay. We can build new decider to decide L complement running D on input omega. Okay. D on omega. If, let's write thinner, if D accepts omega, meaning L, then rejects because omega isn't part of. Okay. If D rejects omega, meaning omega part of L, sorry, then if decider accepts because it's part of L. Okay. Since D always halts and since D and D always, sorry, I forgot English, always halts, thus L complement is decidable. Okay, I will pause my video because my screen recorder doesn't allow me to record more than 10 minutes. Okay, I will remove my work and write question 3 and continue with the question 3. Continue. I have some record issues. Okay. Yes. Show that set a recognizable languages is closed under union. Okay. If A and B are recognizable languages, then A and B also recognizable. It's our statement. Statement is if A and B recognizable languages, then in union B is also recognizable. Okay, why it's true? Because A is recognizable. There is a Turing machine MA that semi-decide A whenever omega under A and MA eventually accept omega, and if omega doesn't accept A, MA either reject or loop forever. Okay, MA reject or loop forever. Similarly, B is recognizable, so there is a Turing machine MB. Okay, same thing. There is a Turing machine MB that semi-decide B. To recognize A union B, sorry, let's close over. A union B, we can build a Turing machine M that does the following on input omega. Simultaneously, it round robin fashion. Simulate MA on omega and MB on omega. Okay. If at any point MA accept, we halt and accept omega. If at any point MB accept, we halt and accept omega. If omega, if omega under A union B, then either omega or omega E. Whichever machine is supposed to accept will do as infinite time, and hence M accept omega. If omega union B, then both MA and MB will never accept omega. Just keep simulating forever and never accept. That's actually that's exactly what semi-decider for A union B should do. Therefore, union B recursively enablable. Okay. Then fourth question. Let's check our time. Okay. Determine whether the language in all Turing machines that accept nothing recursively enablable or not. Let us define more precisely L0 empty. That's L0 contain exactly those Turing machine M whose language accept the string is empty. M does not accept any string at all. Is L0 recursively enablable? To belong L0 machine, M must fail to accept every input. That universal condition for all omega M does not accept omega. Semi-deciders languages typically capture existential statement. There exists an input or condition. Because to confirm existence, you just need to find one example in finite time. In contracts, verifying a universal claim, M accept no input, cannot be done in finite time by using Turing machine. You would have to check all possible input forever and never see an acceptance. There is no point which you can safely say, I'm done, I know it accepts nothing. Form result, LM equal to empty, the emptiness problem. L empty. It's not recursively enumerable, okay. There is no Turing machine that enumerates exactly those Turing machines that accept no string. You can't detect emptiness in finite run if machine might accept something in the future or some other input. Hence, the language of all Turing machine that accept nothing is not recognizable. Okay, not recognizable. Okay, I will pause video because I have limited time. The program just allow me to record under 10 minutes, so that I will pause video and continue with the fifth question. Okay, let's continue with the fifth question. Determine whether the complement of the language of all Turing machines that accept nothing is recursively inalienable or not. Okay. The complement of L0 is L0 complement M LM empty string. Okay, equivalently, L0 complement is the set of Turing machine that accept at least one string. Okay, is L0 recursively NM variable? Okay, NM variable. If M accept at least one string, say omega, then we can deduct that universal search or the evaluating approach. Enumerable all candidate input x1, x2 or x3. Run M each xi, okay? 1, x2, x3, xi. Run M each x for increasingly many steps in round robin manner. If ever we see M accept some x k, then we halt and accept M, okay? This procedure halt within the acceptance exactly when M does indeed accept some input. If M accepts no input at all, this procedure never sees an acceptance and run forever, which is fine for recognizer. Thus, this precisely how semi-decide L0 complement, hence L0 is recursively NM variable. Okay, that's our homework. It was good. Thank you for watching and sorry for late submission.